Welcome everyone to the Med Plus seminar this week. Thank you all for joining. I'm super happy to have David Gamarnik talk to us today about computational hardness in random problems and the overlap gap property. David has been a professor at MIT, I think, for around 15 years now. Some of his work is my favorite work in the community and in math and computer science in general. It's a huge influence for our community of trying to understand computational limits for statistical inference. It has a lot of work in that, and random graphs, high-dimensional statistics, and so on. Just as an example, we were having a group meeting deciding a bunch of papers to read in my group, and I think over half the papers were papers from David. And I'm particularly excited to hear about some provable barriers to actual performing computation on random combinatorial problems. And so please, I'm going to be brief, and without further ado, David, just go ahead.
Yeah, thanks, Afonso, Elias, John, for the invitation. It's a pleasure to give this talk. I gave a similar talk about 2 weeks ago, very similar, about 90% same material. So if you happen to tune up, because I don't see the audience, I have no idea who is in the audience. So if you happen to be at that talk, it's going to be very similar. You just, you just save yourself 1 hour of free time because it's going to be very similar. And as I joked last time, I hope I don't have to give too many of those web-based talks, not because I'm not invited, but because this whole thing is going to be over soon, I hope, as we all hope. So this is joint work with Okush Jagannath and Alex Wine, and while this will be a sort of more of a broader overview of several lines of works on the same topic, but I will focus primarily on 2 papers, one with Okush on approximate message passing, and one very recent with Okush and Alex, and I believe Alex is in the audience, on the low degree polynomial approximation and Langevin dynamics. And as I said, Alex, I believe, is in the audience. He can probably wave, but I don't know if you're going to see him. So if you have tough technical questions, please ask him. Don't ask me. He will be better positions to answer them. Let's see, that works. In lieu of sort of a broad high-level overview, I want to start with with a motivating problem, which is my favorite problem in optimization on random structures, and that's probably a problem that's familiar to most of you. So we consider an Erdős-Rényi graph, G and P. P is constant, like a half, so it's a dense Erdős-Rényi graph. We are looking at the largest clique that is a fully connected subgraph, and it's not hard to show that with high probability the size of the largest clique is going to be twice logarithm with appropriate base of n, of the number of nodes. That can be shown, and can be shown by non-constructive methods like second moment method. It's one of the classical applications of the second moment method that gives you that. So we know, unlike in the worst case optimization problems, in the random structures like random graphs, we often know the answer up front. So that's convenient. We know that the size of the solution to this optimization problem, it's this. What about algorithms? So there is a very simple algorithm to analyze, the greedy algorithm, that finds the size of clique of size half of that. It's indeed very simple to analyze. And it's actually a very naive version of the greedy, in the sense that it doesn't even really try to optimize of the choice of nodes. It's just blindly picks nodes, selects its neighbors, and repeats. I'm not going to go into details of this algorithm, but just wanted to say that it's very simple. So this was known back in 70s, and D. Karp challenged in 1976 in his paper, he challenged the community to find a better polynomial time algorithm. Algorithm that would admittedly not work in the worst case, but at least for the random structures, for the random graphs, would find a better size clique. So improve the factor half that we see here. And sadly, this is still open. Now this is open and quite embarrassing for, I think, a few reasons. It's embarrassing because the algorithm, the best algorithm that we have here, as I said, it's very naive. You're hardly doing any work, but yet improving over this algorithm seems impossible. And all this, heavy machinery that we have developed since then, including convex relaxation and higher level, elevated versions of that, like Lasserre hierarchy, doesn't seem to work. And in fact, it points to the opposite, that none of these algorithms works. And the second reason it's embarrassing is that at the same time, we can't prove it's NP-hard. We don't know that. It's conjectured, but we don't know that. And very briefly, a very similar story with the sparse graph. So if you consider sparse Erdős-Sörényi graph on n nodes, every node has on average d neighbors. And here you consider a slightly different structure. You consider a largest independent set. So independent set, to remind you, is a collection of nodes with no edges in between. Independent sets are more interesting on these graphs because they scale linearly with this number of nodes. Cliques are very small. So that's why I will look at the independent set. And since 1990, we know asymptotically the size, but again, by non-constructive means. The size now is expressed in terms of the number of nodes n, and we know the constant prefactor here, it's expressed here. So we know it asymptotically as the degree increases. We don't know this prefactor for any fixed d. It's a hard problem, but asymptotically we know. And we know what we know in addition is that, again, a trivial algorithm, pretty much the same algorithm, gives you half of that, and nothing better is known. So these are two interesting problems. And I think they are interesting because they are examples of a much, much broader phenomena, where in trying to find optimal solutions for various optimization problems in random structures, because of the randomness, often we can predict the optimal value by some non-constructive means. But when we try to construct the best polynomial time algorithm to actually work on those structures, we fail. We fail within a certain level of approximation, which is problem dependent. For the cliques and independent sets, it's a factor 2. For the problems like random K set, the factor is even bigger, and it depends on the size of the clause. And I have listed here a whole variety of problems, but this is just a partial list. Problems exhibiting a similar phenomena. And unlike in the worst case optimization problem, for these problems on random structures, we can't even prove that they are NP-hard. Now, technically, that would be, in some ways, it would be ideal to prove some kind of an NP-hardness. And it's possible to prove that some problems in random structures are NP-hard. There are many problems in cryptography, like lattice approximation problems, are known to be hard on average. So it's not like hardness on average does not exist. It does. It's just we can't prove that for this list of problems. You might have seen some similar phenomena of the gap between existential objective value versus what can be done in polynomial time in the context in high dimensional statistics and machine learning, and there it comes in the form of this infamous information theoretic versus computation gap. Information theory comes here because those problems involve typically some kind of a planted signal that you're trying to infer. The canonical and famous problem being hidden click here. But let me just say right out of the hand that these are not the class of problems I'll consider today. There is no planted signal. The structure is random structure is fairly symmetric. We're just trying to find an optimal solution on random structures and try to understand why is it difficult. So what's the barrier here? What makes this problem hard? So a great deal of insight came from statistical physicists who don't think of the hardness in terms of complexity theoretic concepts like reduction and NP hardness and things like that. Rather, they try to understand hardness from the solution space geometry or solution space topology. And they argue that the problem on optimization on random structures become hard because the geometry changes in some way. There is some kind of a phase transition. And this was postulated in some other form that that I'm going to introduce here, but through this sort of collective efforts and a chain of connections and implications, the following property that's in the title, the overlap gap property, that originates from the spin glass theory, but under a different name and a slightly means slightly different thing here, that seems to have emerged as a sort of predominant indicator of the hardness. So the property is very easy to describe. Pictorially. I'll give an informal definition in the next slide. And what I want to do in this talk is demonstrate how the property becomes an abstraction, at least for some classes of algorithms. And I'll describe the problem itself and the class of algorithms ruled out by the property. So here's how one can geometrically think about the overlap gap property. So suppose we have a generic minimization or maximization problem, doesn't really matter. It's up to the up to the sign. We have some objective function L here. I'm gonna use my pointer, and I hope it's visible to others as well. Yeah. Okay, Elias.
Yeah, we can see it. Yeah.
Okay, perfect. So we have some optimization function L. We have some solution space capital theta over which we make the choices. So L could represent, for example, the size of the click or independent set. Theta could represent the choices, meaning all independent sets. So L represents the size, and X represents the random structure. So like a random graph or sparse random graph or whatnot. And so the definition, which is semi-formal, but it's a little hard to parse, so I'll give a picture in the next slide, goes as follows. So we say that the model exhibits the overlap gap property if there exists some positive value mu, which denotes the proximity to optimality, and the two parameters nu1 and nu2 such that the following holds. We pick any two solutions, theta1 and theta2, which are mu good, in a sense that they are provided value which is not more than mu from optimality. So we pick two of such solutions. And if it is the case that the distance between these two solutions is either at most nu1 or at least nu2, then we say that there is an overlap gap property. the word overlap says that because instead of the distance, we will be looking at the inner product, which is just a proxy for the distance. It's just a different way of measuring the distance between vectors. So inner product is like an overlap between two vectors. And the requirement is that the overlap is either rather small or rather large with no value in between. Now this is formal definition. Whether it's useful, it's a different story, but it might be hard to parse. So let me give let me give a pictorial description of it. So here's our optimization problem. The horizontal line represents this multi-dimensional set theta. So I represent it as one-dimensional, but it's really truly multi-dimensional set, like a binary cube, over which you optimize. And the vertical line corresponds to the value. So for each theta, for each solution, you have the corresponding value, and you have this landscape of solutions. We're trying to minimize. So there's one point here, theta, which is the best. And what we did next, to remind you, is that we've looked at the space of solutions which are mu optimal up to the mu additive factor. Once you introduce that, you effectively partitioned the entire solution into the clusters of mu good solutions. One cluster is here, another cluster is here, another cluster is here. And so the overlap gap property says the following thing. The distance between any two solutions within a cluster is smaller than the distance between any two solutions from different two clusters. So every size of the cluster, distance, diameter of the cluster, so to speak, is at most nu1, here, here, and here, but the distance between different clusters is at least nu2. Now, for a while, I thought that clustering, and this is actually the first indication of hardness of problem that emerged in the context of random k-set problem. Clustering is kind of the right property to exhibit the hardness. And I thought the overlap gap property is equivalent to clustering, but it's not quite. What's important here is that not just the clusters exist, but the distance between clusters is larger than the diameter within the cluster. And that property allows us to prove things that you would not, at least seemingly, you can't do with just existence of clusters. So this is just a side comment, maybe only makes sense to those somewhat familiar with the literature on clustering for random k-set problem, random coloring problem, and so on. But otherwise, the main thing here is just I wanted to give this geometric description of what the overlap gap property is. I'll continue, but as Afonso said, if you have any questions, questions are welcome. I don't have that many slides, and I'm not I'm going to skip some of the slides that you're welcome to look offline.
I have a quick question. I guess I'm a full data from ETH, doing are you going to explain why it's important that the distance between clusters is bigger than the diameter of the clusters? Or is this the time to ask that?
Yeah, no, it's a good time, but I'll revisit that because that's the key here. The thing is that what's important seems to be important in the sense that it seems to make proofs work. So what's important here is that because the distance between clusters is larger than the diameters of the clusters, this property holds. Because we're arguing not just the existence of clusters, but the distances between two mu near optimal solutions itself being partitioned into smaller or larger values. You see? So if the distance between the clusters, if the distance between the clusters was smaller than the diameter of the cluster, then we would not be able to argue that property.
I guess my question is, why is this important for the proofs?
Oh, okay.
Yeah.
So now why that property is important for the proof, yeah, I'll discuss that in depth.
Okay.
Okay.
So a question also over here from John Niles Weed at NYU. So this definition does not seem to exclude the case where we just have one giant cluster, right? So I guess we want also some statement that there are enough clusters, you know, that they're somehow rich enough. I mean, how should I think about that?
Yes. Absolutely. As stated here, this definition could be useless or even vacuous, because if the nu2, for example, is larger than any largest distance between diameter of the solution space in general, that this doesn't give you anything interesting. So this is still a sort of a definition, but for it to be interesting, it should be the case that some of the distances are smaller than nu1, and some of the distances are larger than nu2. Only then it becomes interesting. And I'll elaborate on that in the context of a concrete problem.
Thanks.
Okay, so with that said, let me introduce the problems that I want to consider for optimizing. Both are the problems are from the p-spin field, spin glass theory, but they're actually fairly easy to state. So I'm not expecting anybody to be an expert in statistical physics. They're fairly straightforward to formulate. So the first problem is optimizing Hamiltonian of the p-spin model in the Ising version. The problem is as follows. Suppose we have a tensor which is n by n by n by n by n p times. Entries of the tensors are IID, Gaussian, mean zero, with the variance normalized in some way that it doesn't really matter why it's normalized that way. It won't be important for the talk.
David, there is another question, if you don't
Yes?
mind. Yeah,
No, go ahead.
By Rafael Mayer. Let me unmute you. Rafael, can you hear me?
Meyer from NYU. So when you were talking about the overlap gap property, we wrote it down as a norm between the theta vectors. We mentioned having a inner product between the theta vectors. So where do the theta vectors lie? Are they in a metric space, a Hilbert space? Like what geometry do we require for the set of possible thetas?
Yes, very good. So actually, in a while, I will switch to the inner product, and thetas typically, or one example is coming up, but typically the solution space is going to be something like a binary cube, n-dimensional binary cube, or Hilbert cube, or sphere. And then typically we will be looking at some kind of a normalization here. So without normalization, you should think of nu1 and nu2 as something like order square root n if it's a binary cube. But for convenience, we will be normalizing those.
Okay, but we should still think of them as being, for instance, on a inner productable space, right? That's an important part of the geometry.
Yeah, there will be. I mean, the inner product will exist because because the solution space we'll look at will be fairly straightforward, like Euclidean cube, binary cube, and Hilbert cube. So let me describe this problem, and the solution space will come up in a very concrete context here, if that's okay.
Thanks.
Okay. So here we have this tensor. It has IID entrance, and right on the question of the solution space. Here, the solution space, we're going to be optimizing over the n-dimensional binary cube. So we're going to choose vectors sigma, which live in this binary cube. And for each vector sigma, we have the objective value, which is the Hamiltonian, technically called Hamiltonian, associated with the vector. But what it really means is that you just take the inner product of the tensor and the vector itself tensorized to power p. Or put it differently, take the inner product of the entries of the tensor and the associated product of the values of the vector itself. And now that maybe that's straightforward, see what it does. But just to help you, if in the special case when p is equal to 2 and A is just a matrix, all you're doing is you're minimizing over quadratic forms. But you're minimizing over quadratic forms where the vectors are binary. So let me pause here and see if there are any questions about the formulation of the problem. It's kind of important that we are on the same page as far as the problem is concerned. Okay, so this is one of the classical, the case p is equal to 2 is called the Sherrington-Kirkpatrick model, in general called the p-spin model. This is a classical optimization problem in spin glass theory. Okay. A very related problem is so-called spherical p-spin model. It's pretty much the same problem. You start with a random tensor, IID entries, Gaussian. By the way, why Gaussian versus non-Gaussian? Sometimes it matters for the proof, sometimes it doesn't matter. Typically doesn't matter for the problem itself. I'm going to stick with Gaussians here, but a lot of these questions make sense and a lot of results extendable to non-Gaussian setting as well. So let's not sweat too much about Gaussianity here, but for concreteness, let's say those are Gaussian. Now the solution space here is different. It's the sphere. So we are heating this tensor A with tensorized points on the sphere with radius square root n. It's a typo here. It should be square root n here. I apologize. Again, when p is equal to 2, that would be minimizing quadratic norm. Now in that case, because you're optimizing on the sphere, for the quadratic case, that problem is trivial because it's just the smallest eigenvalue or singular value if it's non-symmetric. So for the spherical models, only p greater than 2 problem version is interesting. So what do we know about these two problems? What physicists focused on primarily is saying something about the optimal values. And that by itself, unlike the hidden clique, unlike the clique problem, independent set problem that I mentioned earlier, is far less trivial. Second moment method that worked greatly in those problems doesn't work here, provably doesn't work here, but something else needs to be done. And a great deal of development, starting with the work of Giorgio Parisi in heuristics and physics approach, and then formalized mathematically by Talleyrand in 2005. Bottom line being that we know those values of optimization problem for both of versions of the problem. You need to rescale the optimization problems appropriately, and those values known to exist and in principle can be computed. So for example, for the binary version, that's the answer. This answer will be immaterial to us. What matters to us is that these values do exist, probably negative, because we're going to focus on algorithms. So what is the algorithmic goal here? The algorithmic goal is to essentially construct an approximation algorithm. Our input, the data, is tensor A. Our goal is to find whatever is the underlying solution space, be it binary cube, or be it a sphere, or a ball, or whatever other structure you want to look at, is to find a vector that gives you nearly optimal solution with an additive error at most epsilon. So that's the goal. This is the problem that we will be discussing ostensible hardness from the overlap gap property point of view. So what do we know about this optimization problem? In fact, the positive results do exist, and they were fairly recent. One is by Montanari, who solved this problem in a case p equal to 2. So this is optimizing over binary cube quadratic form. He solved this problem positively using approximate message passing algorithm, meaning that for every epsilon here, he constructed solution which is epsilon close to this value. The approach was guided by the non-constructive method of Parigi and Talleyrand, and ultimately boils down to certain message passing iterations that I will describe in the next in a few slides from now. Slightly earlier than that, the problem was also solved for this mixture of spherical p-spin models. So it's not a pure spin model that I've described. It's a mixture in a sense that you take different values of p and you construct a combination of the tensors, and that's your objective function. Let me not go into details of the formulation of this mixture. It's not going to be important for us. For the negative result, it's good enough to stick with the pure case, the one that I have described. So Subak's algorithm is slightly different. It's not approximate message passing. It is rather like constrained gradient descent type algorithm, and I'm gonna leave the details for offline. Both algorithms are motivated by slightly earlier essential algorithm by Bolthausen, which is related to tap iteration that I will also leave for the offline questions if you have. It is these two problems, or rather one problem with two different solution spaces that I want to describe from, now discuss from the hardness point of view. And now let me give the formal definition of the overlap gap property, but in the context of this problem. It is very similar to what I have already introduced, with one caveat. Rather than considering one optimization problem, here we will consider a family of optimization problems. So we generate two independent tensors from the same distributions, A and A hat. And now let's create the following natural interpolation between these tensors described in here, where tau varies between 0 and 1. Why do we choose this particular form of interpolation? For the very simple reason, for every value of tau, A is still a tensor with Gaussian entries with the same distribution and still IID. So in other words, we have this kind of a natural continuous flow from A to A hat. And now the definition. Looks a little busy, but hopefully it's not too different from the one I gave earlier. We say that this family satisfies the overlap gap property. This entire family satisfies the overlap gap property over whatever is the solution domain Xn. Think of binary cube or sphere. With this parameters mu proximity to optimality, nu1 and nu2 same as before. It measures upper and lower bounds on the overlap. If it is the case, if the following holds, you pick tau1 and tau2, in other words, the indicators of two instances from this family of interpolated family of instances, tau1 and tau2. These two instances could be, there's no restriction on them. They could be identical. Tau1 could be equal to tau2. Or one could be 0, one could be 1. So no restriction on tau1 and tau2. Pick any two solutions where the first solution is mu optimal with respect to the first instance, and the second solution, sigma 2, is near optimal for the second instance. if it is, we say that the overlap gap property holds if the normalized inner product of these two solutions is either at most mu1 or at least mu2. And here, on the earlier question of how should it, when is this definition useful or not, now you see here is that if you take the solution sigma 1 and repeat it, then this value is 1. So this definition is interesting only when mu2 is indeed less than 1. So this is the definition of the OGP that, depending on the setup, we can either prove that it holds or at least conjecture that it holds with the good backup reasons for the conjecture. Let me stop here and see if there's any questions about this definition.
This is again Afos Bandeira from ETH. I just wanted to ask you if, in the case when tau 1 and tau 2 is 1, 0 and the other 1, the two problems shouldn't have information about each other, right? So then is the inner product just always 0? Because this is a like statement in high probability on the quench draw of the problems?
Yeah, absolutely. So if tau 1 is 0 and tau 2 is 1, then we have two independent instances. In that case, it only makes sense that sigma 1 and sigma 2, they optimize two completely independent instances. They should be nearly orthogonal. And that's the case, indeed. And in that case, this value will be not just at most mu1, but in fact, it's going to be pretty close to 0 with high probability. And that's important. That's actually important that at the extreme of this interpolated family, that you have inner product which is close to 0. And at the same time, if tau 1 and tau 2 both are equal to 0, let's say, then you can simply take sigma 1 and sigma 2 to be the same. And in that case, as I said, their inner product is 1. So the fact that you sort of can achieve, almost for trivial reasons, 0 and 1 here is crucial for the proofs of the negative results.
So intuitively, should I think of maybe the problem has one Bayesian slightly lower than the other, and as you interpolate, the Bayesian swap, and that's what creates this gap?
Yes.
Something like this. Okay. All right. Thank you.
Yeah, that's precisely the way to think about it. Good. So let's continue. So what do we know about the property? Sometimes it's proven facts. Sometimes it's conjectures. Depending not only on the objective function, the objective value here, the data is always p-spin. I'm not going to switch from p-spin model to anything else. It's always this Gaussian tensor. But the solution space might change depending on the problem. Sometimes it's a binary vector. Sometimes it's a sphere. So it turns out, again, I apologize for the error here. It should be square root n. So it turns out that for the binary version, so when you optimize over the binary cube, as long as p is at least 4, then the overlap gap property does hold for some parameters mu1 and mu2 that are not optimized in the theorem. We just know that that's the case. So both binary, not just binary, but in the sphere case as well. As long as p is at least 4, both models exhibit the overlap gap property. Now for p is equal to 2, which is only interesting for the Ising model, this is the binary case, it is just conjectured that it does not exhibit OGP. And I want to go back to the Montanari's result. Not only it's conjectured that there is no OGP, something even stronger is conjectured. That roughly speaking says that if you pick any two nearly optimal solutions for this problem and look at the distributions of their overlap, appropriately defined distribution of the overlap, this distribution has a continuous support. So its support is the entire interval. That is conjecture, which is widely believed in physics, and that's the conjecture that Montanari adopted to make his proof work. There's very little doubt that this conjecture is true, but what I think is important and what sort of raised our suspicion that something might be connected with OGP is that that conjecture implies something stronger than the lack of the OGP, if that makes sense. So if this conjecture true, then for sure OGP doesn't hold, but it's not equivalent. It's actually slightly stronger. Let me go find my place. Okay, so this is what we know about the OGP for these two solution spaces. For the context of the approximate message passing algorithm, I want to introduce a third solution space here. And I promise it's the last solution space I'm going to discuss.
David, just one question. This is Elias Adik from NYU. Like you said that like the property of Andrea's paper is stronger than, it implies like something stronger than OGP. Do we know this or we believe this is the case?
Oh, so, okay. So,
like if you know.
So, I mean, it's the implication is straight, is it strictly stronger or not? Well, I have to think what it means. So it basically, it says that not only the overlaps span the entire intervals, but there is a positive density on this. So if you think about the distinction between the two, it basically has to do with the limit of the overlap distribution. So in other words, not only the overlap distribution has a positive support, but does so is positive in the limit as n goes to infinity. It's a slightly subtle point. You're probably getting it, Elias, but it's slightly subtle point to elaborate on here. So technically it's stronger. Whether it's actually stronger or equivalent, I really have to think about that properly. Okay, so back to this. So here, if it is a Hilbert cube, so in other words, we optimize over the Hilbert n-dimensional Hilbert cube over in our tensor. We only have a conjecture that it holds when p is at least 4 and does not hold when p is at least p is 2, similarly to the binary cube. But unfortunately, for this version, I have to say that this version has not been widely analyzed by physicists because we just use that with Okush Jagannath to discuss the approximate message passing algorithms. But it's very reasonable, and we have some evidence why this still should be true even in this solution space. So now let me describe the class of two classes of algorithms that are ruled out by the existence of OGP, and then I will wrap up. I actually don't have that much time, right? I have, what, 5 minutes left?
Yeah, well, you can take a few more, it's fine. You can take 10 minutes for sure.
Okay, I'll try to be conscious of that. So the slides are going to look a little busy, but you don't have to understand all the details on that. So approximate message passing algorithm, the general formulation of it is very tricky and it's not sort of existent in the literature. So we had to sort of invent with Okush on kind of on the fly what it looks like. So I'm going to introduce one definition here, which just seems to include the previous definitions used in the literature, including Montanari's and previous work. So basically, it involves several types of operations which are allowed to construct the solution. The first operation is described here. It's a operator based on a tensor. Think of it simply as linear operator in case p is equal to 2. If you have some vector x, you multiply it by the matrix x, A. In case of the tensor, you have to do something more complicated, described here. It's an operator that maps n-dimensional vectors into m-dimensional vectors, simply as that. Another thing that we're going to use heavily is some choice of nonlinear transformations, which will be applied coordinate-wise. So these nonlinear transformations, if you ignore value t here, think of it as just taking some value between minus m to m and creating another value which is going to be also in minus m to m, like taking logistics functions or taking hyperbolic functions and something like that. The choice is immaterial to us because we're going to be allowing any kind of a transformation which is Lipschitz continuous. It is important for positive results, but not so much for the negative results. So approximate message passing algorithm, it needs to initialize somehow. So let's say we initialize this vector of all ones, and it works as follows. So imagine you build a series of solutions over the time in t, capital T steps, that basically combines this, applying these non-linearities and linear transformations that I've described. This is, and additionally apply some truncation to make sure that the vector always lives in, always has bounded L infinity norm. So basically what this describes is that is something like this. You've constructed your solutions, candidates of solutions up to t minus 1 to construct a solution at time t. You do a combination of multiplying by applying this operator A and applying these nonlinearities, capital F and little f, locally. That means that those functions are applied for each coordinate of your vector. Why? Because that seems to be working in the positive results. And this, so anytime you have iterations like this, we'll say that we have an approximate message passing algorithm. Any questions now? So one final step is because this space of solutions, sequence of solutions lives in the slightly higher cube, at the final step we'll have to truncate it back to the Hilbert cube. So whatever is bigger than 1 has to be truncated to 1. Okay, so now I'm going to state our first main result. It's probably something anticipated as I was sort of guiding you morally to that. The result says that for models, for the piece, okay, let me give the results. So as under the conjecture, and unfortunately it's only conjecture, that OGP holds for the Hilbert cube, the solution anytime when P is at least 4, we assume the overlap gap property holds, any choice of truncation horizon T and choices of nonlinearity will result in a solution which is mu suboptimal with respect to objective function, where this is the same mu as comes from the overlap gap property. So this theorem is the complementary to the positive result by Montanari, up to some technical nuances that I will skip. And so let me pause here and see if any questions about that.
Yeah, this is again Alphonse Valera from ETH. Is this dependency on mu the correct one, in the sense that could one hope to show that the positive result, that there's if no overlap gap property for a certain up to a certain mu, that you could get to that kind of optimality?
There is something towards that. There is a paper by Andrea and co-authors showing something related. So they can quantify the success level of approximate message passing algorithms, and they quantify this proximity. But I'm not sure it's exactly the value that I don't think it's overlap gap property value. I think it's something else. To be honest, I have to understand it better. Maybe I don't know if Alex knows the answer here better than I do. Yeah. So there's a step in this direction. So that maybe that's the answer. Not a very satisfying answer, perhaps, but.
Thanks. I unmuted Alex too if he wants to say anything.
Okay.
Hi, can you hear me?
Yes.
Okay, yeah. Right, I think that, right, Andrea's new results with Ahmed El-Alawi and Mark Selke, right, they use kind of AMP state evolution to say exactly what threshold it will go to. Whereas I think OGP is only known to hold in kind of a small neighborhood around the optimum. So it's kind of like there exists some epsilon so that you have OGP in some small neighborhood of the optimum. But I don't think it's known like exactly where the OGP starts to hold. Does that seem right, David?
Yeah, no, that's right. But how do they quantify? I just don't remember how they quantify the gap that they show the AMP converges to some value. What is this value that they quantify? I just don't remember the nature of this value.
Oh, it's like given by some AMP state evolution equations. So it's not that explicit, but you could solve, yeah.
Yeah. So I guess at this stage, the only thing, right. So thanks, Alex. I think the only thing we can say is that that value has to be smaller than or larger than mu. But Alex is absolutely right. We don't even know what precise value of mu is. We just know that for mu small enough, OGP holds, but we don't know the exact value of that.
Thanks.
Sure. So, okay, so let's continue. And the next class of algorithms that's based on a paper which is yet to be posted with Alex and Okush, is in the context of the low degree polynomials. One thing I will for sure fail in this talk miserably is to give you proper background for the low degree polynomials and why they're interesting. So instead, I will refer you to Afonso and Alex and other experts on this field. I'll just say that the low degree polynomials come up widely in studying of the planted structures like planted cliques problems, in trying to understand the hardness of those in inferring the signal. Not so much in the unplanted version, but it's only very natural to try to see what's the power of low degree polynomials. And one motivation for that, and another motivation for that, is that it seems that low degree polynomials encompass many other problems, including message passing algorithms. Not quite formally yet, that has to be sort of sorted out, but intuitively it includes many other classes of algorithms. So this seems like the broadest class of algorithms that that have been analyzed in the past. The formulation of the problem of the algorithm is rather simple. It's suppose we have somehow you construct a sequence of n polynomials, because we need to construct the n-dimensional solutions. We construct a sequence of n polynomials, and each of these polynomials is degree bounded by d, and the values that we will plug into polynomials will come from the tensor entries. So in other words, if we apply this vector of polynomials to tensor, what we do is that we construct this vector. Each coordinate is just polynomial evaluated at some entries of the tensor. So that gives you a vector, and then that gives you this vector described here, and then we evaluate the quality of this vector by the tensor and see how good we do and hope for the best. And as I have sort of suggested earlier, this approach, this class of algorithms is also ruled out. The semi-formal statement of the result is here. I'm skipping some technical details that will be very difficult to sort of discuss in the real time. But let me just say that what effectively this result says, and in a way it's slightly different from previous one, is that this result requires that the algorithm has a high probability promise. So in other words, what it says is as follows. Suppose you manage to construct polynomials that when you evaluate them, they succeed up to threshold eta with high enough probability that depends on the degree of the polynomial. So in particular, if the degree of the polynomial is order n, which is the size of the tensor, you require that these polynomials succeed to get a value below theta with modulo exponentially in n small probability. And then the result says that with this high probability promise, you cannot do better than mu, again, mu away from optimality. This high concentration, in other words, high concentration algorithms constructed based on low degree polynomials cannot overcome the overlap gap property barrier. Right, and since I'm practically out of time, let me just say that a third class of algorithms that I don't have time to discuss is vanilla Langevin dynamics on a sphere. The result is of this similar nature. Langevin dynamics fails to find optimal value mu optimal value with the same value coming from the overlap gap property. I have a few slides on proof technique that unfortunately I don't have time to go over, but Afonso actually earlier more or less articulated the idea. The idea here is the key property here that we use is stability. The stability says that these algorithms share the stability property in the sense that perturbing the instance of the problem does not perturb the solution that much. In other words, if you change your input A a little bit, the output, the algorithmic output should not change much. So it has a continuous property. And this continuous property can be used against the overlap gap property in the sense that if this algorithm succeeded, at some point, they would have to construct two solutions that fall into the forbidden interval, nu1 and nu2. Essentially, so stability provides the continuity property that goes in contradiction to the discontinuity exhibited by the overlap gap property. So, and that's all I'm gonna say here. In the last two slides that I'm gonna these are just references, give you the list of problems and algorithms ruled out by OGP. On this slide, this is for the unplanted structures, and here is the list of more recent works on planted structures such as sparse PCA. So I've mentioned Ilias's and Alex's and Benaru's work. I'm not sure the paper is out yet on arXiv, but I assume it's going to be posted sometime soon. And I apologize for going quite a bit over time in this talk. So let me stop here and thank you.
All right, thanks for the great talk.